Anomaly detection is the task of finding anomalous points or outliers in a dataset. Real-world datasets where we are interested in finding anomalies are often very high-dimensional, but can still be well approximated by low-dimensional projections. Much of the signal in the data often lies in this lower-dimensional subspace. This idea leads to a popular class of anomaly scores known as PCA-based anomaly scores. Principal component analysis or PCA finds the best linear low-dimensional representation of the data, which often captures a large part of the signal in the dataset. The idea behind PCA-based anomaly scores is to model the data points to be approximately low-dimensional or approximately Gaussian, and classify points which deviate significantly from these assumptions as anomalous. Let's look at these scores more closely. Suppose the dataset is three-dimensional, and the principal subspace is the two-dimensional subspace shaded in red. For a data point AI, consider its projection A parallel onto the principal subspace, and its projection A perpendicular orthogonal to the principal subspace. Our first anomaly score is the projection distance, which models the distribution of the data to be approximately low-dimensional. The projection distance of a point is just the distance from the low-dimensional principal subspace. The second anomaly score we consider is the leverage score, which models the distribution of the data projected onto the principal subspace to be Gaussian, and classifies a data point as anomalous based on the likelihood of the projection A parallel onto the principal subspace. What happens when we use these scores on real data? We show the top 5 anomalous scores for each digit on the popular MNIST dataset based on projection distance in this case. And here are the top 5 anomalous scores for each digit based on leverage scores. The advantage of PCA-based anomaly scores is that they have a rigorous mathematical justification and provide a clear explanation for why a data point X is anomalous. But the disadvantage is that the time complexity for performing PCA scales quadratically with the dimensionality of the data, and this is problematic for high-dimensional time series data. The question that we address in this paper is if we can have the benefits of PCA-based anomaly scores without paying the full price of full-blown PCA computation. In this work, we answer this in the affirmative using tools from matrix sketching. Sketches are low-dimensional encodings of data points that are much cheaper to compute than PCA. In fact, they only require time linear in dimension versus quadratic in dimension. These sketches were known to preserve basic geometric structure, such as pairwise distances, but we show that they also preserve higher order geometric structure, such as closeness to a low-dimensional subspace or distance from it. These ideas lead to faster algorithms which also use less space, but still have rigorous theoretical guarantees.